In this video, we'll talk about the fifth assumption of homoscedasticity, which has direct implications for the variance of our estimators. So recall that in the simple linear regression model also we talked about this assumption, which basically says that the variance of u, which is our error, does not change with any of the x's, right? So here we are basically saying if we were trying to, let's say, estimate the effect of income on savings, we basically want that the variance of savings, ultimately we've proven in the previous chapter that variance of u given x is equal to the variance of y given x, right? So we basically know that the variance of savings given income equals, let's say, $100,000 should be equal to the variance of saving given income of $25,000. Okay, so that's what the idea is here. Okay, so we're basically saying that the variance of the error u does not change with any of these of the x's. Okay, now in some cases you might find this to be unrealistic, but this is the assumption that that would have direct implications for the variance of our estimators. Now here we say that this assumption can never be guaranteed. Okay, so it really depends on the model that we are working with. Okay, so now remember that we needed the first four assumptions to prove unbiasedness, and if we add a fifth assumption of homoscedasticity, where the variance is given by sigma square, these together are called Gauss-Markov assumptions. Okay, now we want to discuss the efficiency of our estimators, okay? But for now, we will only focus on the slope coefficients because that's what's more interesting to us. So there are at least two things we want to discuss before we get to the formula for the variance of beta 1 hat. Now, the first thing is something we discussed even in the last chapter, which is the total variation in x, right? So the total variation in x, any xj can be measured as the deviation of xij from its mean, and you square it and you sum it across the sample. So if you kind of manipulate this, you can say that SSTJ divided by n is just the sample variance of xj. The second measure that we are interested in is going to be important because we're going to call that Rsquare J. And this is basically, it's not your traditional R square, so keep in mind that this is going to be interpreted as the R square that you get when you regress xj on all other x's, okay? So the j corresponds to that particular variable xj, okay? And really what you're trying to do here is to understand how much or how strongly are the independent variables related, okay? At least the linear relationship, the strength of the linear relationship. That's what you're trying to measure. So remember that we said in MLR3 that we do not, the assumption says that there is no perfect collinearity between our x's. No perfect collinearity or no perfect correlation. So in other words, we can basically rule out the fact that, or rule out this measure of R square J that equals 1, right? So if you regress xj on other x's, right, R square J should not equal 1, okay, because of that assumption MLR3. And this means that basically we are going to be left with an R square J which is less than 1, right? Greater than or equal to 0, but less than 1. Okay, and as R square J gets closer to 1, this indicates that xj's are more linearly related to other independent variables. And that's not a problem, but this is going to have some implications for the variance of beta j hat. So now let's talk about this theorem which says, which tells us something about the sampling variances of our slope estimators. So there is this formula which says that the variance of beta hat j equals sigma square, which is the same as what we had in the simple linear regression case, the total variation in xj, and then there is this other term that appears here, which is saying this is that the denominator also has 1 minus R square J, right? So R square again is not our traditional R square. This is basically the R square obtained by regressing xj on other x's. This is what you want to remember. Okay, so let's take these one by one and understand what are the implications of this. So what factors affect the variance of beta hat j, or the efficiency, in other words, the efficiency of this estimator, of the slope estimator? Okay, so remember the formula, right? So we're basically saying this is our right? So if this is our formula, then we are saying that we want the variance of beta hat j to be lower, right? For our estimator to be more efficient. So in order to get this left-hand side to be lower, it is governed by at least 3 things on the right-hand side, right? These 3 things. So let's take a look at these one by one. So the first thing is the error variance. Okay, so as sigma square decreases, as the numerator decreases, the variance of beta hat j would decrease. And one way to reduce the error variance is to take more stuff out of the error. So basically think about adding more relevant explanatory variables into your regression. Okay, so adding more x's, relevant independent variables would help this. The second is this guy right here in the denominator, which is measuring the total sample variation in xj. So as SSTJ, or the total variation in xj, increases, as the denominator increases, right, this increases, variance of beta hat j would decrease. Okay, and so we've talked about how to do this even in the second chapter, right? So this goes down or this goes up, both would cause variance of beta hat j to go down. Okay, so remember that SSTJ is basically a function of your sample size. So one of the things you can do is you can increase your sample size. So you can increase the sample size and therefore increase the total variation in xj. And the third factor that affects the variance of our estimator is R square J. So as R square J approaches 1, the variance of beta hat J tends to infinity. Okay, so remember that R square J is measuring how linearly dependent is xj to other explanatory variables, right? So it has nothing to do with y. It's all measuring everything in the strength of the relationship between the different x's. Okay, so you can almost see here that the smallest variance for beta hat j would be the case where R square J equals 0, right? So if the variance was just given by this formula, which is really your simple regression formula, that is when the variance would be the lowest. Okay, but we don't really encounter that very often. Okay, so R square J is very, very rare. Okay, even small values of R square J aren't very common. And in fact, R square J closer to 1, so not equal to 1, but closer to 1 is somewhat common. And this can sometimes cause some problems for getting some precise estimate of beta hat J, of beta J. And here's a graph that's showing you this nice relationship between your R square J. As R square J goes from 0 all the way to 1, you can see that the variance, which is measured on the y-axis, the variance of your estimator just increases, right? So here this is going to approach infinity. So whenever you have R square J close to 1, this is called the problem of multicollinearity. So if your x's are highly correlated, then you have this problem of multicollinearity. Okay, and that is going to have some implications on the efficiency of your estimator. Okay, but the important thing to note is that just because your x's are highly correlated, this does not violate any of the Gauss-Markov assumptions. Okay, so remember that sometimes when it's said that multicollinearity occurs when there's high correlation among two or more variables, sometimes people make this claim that this is violating some of the assumptions that we made. So it is not violating anything. Okay, and also to note that as long as the zero conditional mean assumption, which is to say that the expected value of u given x1, x2 through xk equals 0, if that is met, the OLS estimator is unbiased. Okay, so we only need those first four assumptions to hold. But if it is not going to be holding, then, or if it is violated, then this is not unbiased. Now, remember that we do not need, even if we have multicollinearity, if our x's are highly related, this does not cause the OLS estimators to be biased. Okay, so we will still have this theorem of unbiasedness hold. Also, any claim that the OLS variance formula is somehow biased in the presence of multicollinearity is also wrong. So remember that. The formula is always correct. The formula that we just described is going to hold if these five assumptions, the first five assumptions or the Gauss-Markov assumptions hold. The only thing that we define here, another term that we define here is called the variance inflation factor. And this is just the ratio, this ratio of 1 over 1 minus R square J. So you basically can interpret this ratio as something that's inflating the variance of our estimator. And that's why it's called the variance inflation factor. It's basically increasing the variance. Okay, so as r square becomes closer to 1, the variance inflation factor increases, right, and can go to infinity. Now, sometimes, there are some sort of rules of thumb that you should try to remember when you do your empirical projects. So when should we be concerned? What should be the value of the variance inflation factor when we start getting concerned? So if the variance inflation factor is greater than 10, which is saying that r square j is greater than 0.9, then yes, this can pose some problems for the efficiency of our estimator. Okay, so we typically would want to have r square j smaller. But you can try to, even if you have a large variance inflation factor, you can always try to offset it by a large variation in xj, right? So if you have a large sample, that is one way to counter this problem of a higher variance inflation factor. So a large sample size always helps.